Okay, here's a problem about limiting reagents. So if 0.4 moles of hydrogen and 0.15 moles of oxygen were to react as completely as possible to produce H2O, what mass of reactant would remain? So we've got some molar quantities, but let's get our bearings here. We're going to be talking about stoichiometry, so we need the balanced equation. So hydrogen and oxygen are producing water, right? So we got to balance it. We've got two oxygens, one oxygen over here, so we got to put a 2 there. Now we have 4 hydrogens and just 2, so we need to put a 2 there. So this is balanced. So what we're understanding is that hydrogen and oxygen react in a 2-to-1 ratio. So if we have 0.4, let me put that in a different color so it's a little easier. 0.4 moles of hydrogen and 0.15 moles of oxygen, which one is going to be the limiting reagent? So 0.4 moles of hydrogen could react with precisely half as much oxygen. So 0.4 moles hydrogen could react with 0.2 moles of oxygen, and we do not have that much, right? We have less than that amount. Oxygen is going to run out first, right? Similarly, 0.15 moles of oxygen will require 0.3 moles of hydrogen to react completely, right? We double it. So 0.15, 1 to 2 ratio, 0.15 moles, we need 0.3 moles of hydrogen, and we do have that. We have more than enough. So clearly, whichever way you want to approach this, oxygen is the limiting reagent right here, right? It's the limiting reagent. It's going to run out first, and therefore we're going to have hydrogen in excess. So what mass of reactant would remain? So no oxygen, because that's a limiting reagent, so that goes to completion. But if 0.3 reacts, right, we start with 0.4 and we use up 0.3 to react with oxygen, we're going to be left with 0.1 moles. This is the excess reagent, or the reagent in excess, and this is the amount of excess that we're left with. 0.3 react, 0.1 is left. So, but it asks for a mass of reactant. So 0.1 moles of H2 times 2 grams per mole, right? We don't have to worry about sig figs right now, but we know H2, hydrogen is 1, there's 2 of them, 2. So that is going to be 0.2 grams of H2. So that will be A right there. So number 1, we had to write the equation and balance it. And then 2, we had to figure out which one was the limiting reagent. We have to compare, right? That's why we needed balance, because we need the stoichiometry. For every oxygen molecule, we need 2 hydrogen molecules. So 0.15 moles, that was good. That was the limiting reagent. Then we just found the leftover, right? The excess reactant, convert to grams, and we're done. So that was a nice one regarding limiting reagents. Okay, this time we've got sort of a 3-part question. So this is part 1. We're going to be talking about the same reaction in each case. The first one says, we have a 0.5 gram sample of magnesium solid, and we're placing this in a hydrochloric acid solution, and it reacts completely. So the hydrochloric acid is in excess. Now, which of the following equations best represents the reacting species in the reaction described above? So what is happening? We need to recognize this kind of reaction and realize that when we have a solid metal and we're reacting with a Bronsted-Lowry acid like hydrochloric acid, what we're doing is we're going to be producing hydrogen gas, right? This is a redox reaction. And so the chloride is actually a spectator ion. So what we need to look over here and see. Well, some are going to be nonsensical. We know that we're not producing chlorine gas. That doesn't make much sense. We also know that magnesium chloride, that's not going to precipitate, and it is just spectator ions, right? We just kind of need to be familiar with this kind of reaction. What we're understanding is that magnesium has 2 valence electrons, and so 2 protons each are going to pick up one of those electrons to produce the magnesium 2 plus ion, and we're getting hydrogen gas. Right, this should be a very familiar reaction. You could see this with zinc, you could see this with other metals, and we just need to know that it is a very common reaction to react solid metal with an acid like hydrochloric acid to get the metal cation and hydrogen gas. Okay, and so this is a redox reaction. Chloride is a spectator ion, and so this is something that we should be familiar with. So those are the species, those are the reacting species here. So now that we know that, let's check out the second one. So we're doing the same experiment, but we're taking a small piece of magnesium, placing it in a flask containing excess 1 molar hydrochloric acid. Now you want to determine the number of moles of gas produced. We want to get quantitative data about the moles of gas produced. So which is the best way to do this? Which is the best way to get this data? So A, conducting the experiment at different temperatures to see which generates the most gas. So that doesn't really make sense, right? First of all, this doesn't say anything about data collection. It's just saying we're just modifying the temperature. It doesn't explain how we're going to be getting data about moles, right? Now, B says completing the entire reaction in a large Erlenmeyer flask of known volume to measure the volume of gas collected. So this is saying to measure the volume of gas collected, which is something that we're going to want to do. However, how would this work in a large Erlenmeyer flask, right? We can't be using an open vessel because when you're producing a gas, the gas is going to evolve and then it's going to leave. If you have an open reaction vessel, it's going to leave the vessel and then you cannot take any kind of measurement. So that's not going to work. And actually D is the same, right? Conducting the reaction in a graduated cylinder and measuring the volume of the gas collected. How are you going to measure the volume of the gas collected if you have a graduated cylinder? The gas is going to leave the vessel, right? So that by process of elimination, of course, we're talking about C, collecting the gas in a U-diameter tube and measuring the volume of the gas collected. Now, so even if you don't really remember what is this U-diameter tube, first of all, the word tube is kind of a tip-off, right? A tube is not, it doesn't sound like it's going to be open to atmosphere the way a graduated cylinder or an Erlenmeyer flask would be. And that is how we're going to measure the volume. So what this is you're allowing a reaction to occur, and then you're letting the gas go through a tube and up into through some smaller tube and up into an inverted tube where you have some fluid, some water, presumably. And so you have gas up above that, and then the more gas that's produced, the more that pushes the water down that tube, so you can actually get a volume reading. And then through ideal gas relationships, we can go from volume to moles. So definitely volume, right? 3 of them say volume. We're measuring the volume, right? So obviously that's what we want to do. That's why A doesn't make any sense. A is the obvious one that doesn't fit, right? But then, yes, we definitely want to get the volume of the gas, but how are we going to do it? Which vessel is appropriate? So hopefully, even if you didn't remember what a U-diameter tube is, you could rationalize that Erlenmeyer flask and graduated cylinder. That's not going to work. The gas is just going to go away. So that's that one. And then finally, we want to talk about, if we're doing a third experiment, we've got 0.10 gram samples of magnesium, and we're placing these in excess hydrochloric acid of different concentrations. So 0.05 molar, 0.1 molar, 0.25 molar, and 0.5 molar. The reactions are run in successive order from 0.05 to 0.5, and the time required for each reaction to go to completion is recorded. As the concentration of hydrochloric acid increases, which of the following is the expected result? So reaction time, increase or decrease, and the rate of reaction, increase or decrease. So when you start this reaction, when you toss that magnesium metal in there, how fast is it going to go, right, depending on which concentration we're looking at, and then how long does the whole thing take? So what we need to understand is that as the concentration increases, there's more of the species in there. There's more of the reacting species in there, right? We have more hydrochloric acid, so we have more protons available to accept those electrons, and so the rate of reaction is going to increase as concentration increases, right? That's just a general rule of kinetics. You increase the concentration, it's going to go faster, because what you're doing is you're increasing the probability of reacting species colliding, right? If you have only very, very few particles, it's going to take a long time for them to float around and find each other to react. But if it's jam-packed with the reacting species, they're very rapidly going to find each other and react. So the more concentrated, the higher the concentration, the faster the rate of reaction. So definitely rate of reaction decreases. That doesn't make sense. Right, rate of reaction increases. Then the reaction time, does the reaction time decrease or increase? Well, it's going faster, right? And we're using the same mass of magnesium in each case. So if you have the same mass of magnesium in each case, whichever one is going the fastest, it's going to finish first also, right? So definitely we're saying that the rate of reaction increases, but the reaction time decreases. It happens faster. It happens in a shorter span of time. So the more concentrated the acid, the faster it's going to go, and thus the sooner it's going to be done. So that is definitely B right here. So that's a little bit about this type of reaction, reacting a solid metal with a Bronsted-Lowry acid to produce hydrogen gas, and then a little bit about data collection, a little bit about kinetics, just making you think about different aspects of this kind of reaction. Okay, we have a couple multiple choice problems looking at the periodic table. So we have three statements and then some different options about groups or sections of the periodic table that we want to assign here. So number one, elements that are the most difficult to oxidize in a given period. So a period is a row, and oxidizing is a loss of electrons. So which ones are the hardest to remove electrons from? So when we're removing electrons, we're looking at ionization energy. So we're asking which are the elements with the highest ionization energies in their period. And so remember, ionization energy increases going to the right along the table. So on the left, this first group here, these have very low ionization energies. They only have one valence electron, so it's very easy to remove that electron from that shell. But as we go to the right in the period, we're adding protons to the nucleus. So we have a greater and greater effective nuclear charge. Those electrons in that shell are being held more and more tightly. That's also why the radius contracts. But so if it's harder and harder to remove electrons as we go to the right, then obviously the noble gases are going to be the hardest to ionize. And thus the hardest to oxidize. So it's the hardest to remove these electrons. That's also why the noble gases are so unreactive, right? Helium, neon, argon, even krypton, they don't really do any chemistry. Xenon can make some covalent bonds, but for the most part, these are inert. They're the inert gases. They're the noble gases. So number one is definitely going to be A, noble gases. Two, elements that are always radioactive. And so they say always radioactive because most elements have one or more radioactive isotopes, right? Carbon-12 is not radioactive, but carbons 13 and 14 are. But so elements that are always radioactive. Elements that are always radioactive, not just isotopes that have an unfavorable proton to neutron ratio. We're talking about elements, nuclei that are just so big. Because when you have nuclei that are so big, they're inherently unstable, just because the strong nuclear force holding the nucleons together is overwhelmed by the electromagnetic repulsion pushing all the protons apart. So once you get a really big nucleus, it doesn't really matter what the proton to neutron ratio is, it's going to be unstable. So which are the biggest ones here? Noble gases, alkali metals, halogens, transition elements, or actinides. So remember, here's the lanthanides and here's the actinides, the ones starting with actinium. So these are atomic number from 89 to 102. These are big. In fact, most of these do not occur in nature. Above uranium or so, these are strictly man-made, synthesized in particle accelerators. And they're so big that they very rapidly decay because they're unstable. So that is definitely going to be E. The actinides are always radioactive. Now, three elements that are most likely to form anions. So when an element forms an anion, it must have gained electrons, right? Anions are negatively charged ions. And so it must have gained electrons, so we're looking at electron affinity. Okay, and electron affinity also increases going to the right, increases going up and right. So the only thing is that we exclude the noble gases there because they are inert. They have a full valence shell. They are not going to be able to accommodate more electrons. So we're really looking at the halogens as having the highest electron affinity. So fluorine, chlorine, they have very high electron affinities. They're very, very likely to form anions. They're very ready to gain one electron to become a fluoride ion, a chloride ion, right? Any of the halide ions. So the halogens have the highest electron affinity because if they get one electron, they attain noble gas electron configuration, which is very stable. So halogens are most likely to form anions. So this was good looking at the periodic table, making sure that we know the properties of certain groups or regions of the table, and then talking about oxidation or ionization, electron affinity, and radioactivity. Okay, we have a problem here with the periodic table, some substances, and we want to assign these substances to these three statements. So let's take a look at these. Molecules with a pyramidal shape. So we're going to want to draw these. We need to know about Lewis structures and also Vesper theory. So NH3, nitrogen has 5 valence electrons, right? 1, 2, 3, 4, 5. 2s2, 2p3. It's got 5 valence electrons. And so that is going to make 3 bonds in one lone pair. And what that means is that this has a pyramidal shape. So we got that one right away. Right, so this lone pair is an electron domain. Nitrogen has 4 electron domains. This bonding pair of electrons, this one, and the lone pair. Those are all electron domains. And so with 4 electron domains, we've got sp3 hybridization, which means a tetrahedral electron domain geometry. So we have these roughly 109.5. It's a little of what like 107, but they're close to what methane would be, right? And so because this lone pair is pushing those other groups away, we end up with this pyramidal shape. So 1 is going to be A. We may as well just make sure we understand why BH3 doesn't work, however, because boron has 3 valence electrons. That is 2s2, 2p1. So since boron has 3 valence electrons, it can only make 3 bonds, and then it does not have any electrons left over. Right, so boron is sp2 hybridized. It only has 3 electron domains, so this is trigonal planar. So that looks like that. That is planar. That's flat. It's a flat molecule. It is not pyramidal. Then H2 doesn't make sense. That doesn't have a central atom. HBr does not have a central atom. Those are diatomic molecules, so we would not assign geometries to those. And then SH2. SH2 is like water, right? Sulfur is an analog of oxygen. So the best way to show this, actually, well, now we could just do this, right? SH2. This is just like H2O, right? So it's like ammonia and methane. So to go from methane to ammonia, we remove one bond, put a lone pair. And then to go here, we remove another bond, put another lone pair. So this is very similar to water. So we would call that bent, not pyramidal. Okay, so that one's definitely A. Now, 2, strong electrolyte in aqueous solution. So what are the things that are going to be strong electrolytes? It means we have ions in solution, right? And so obviously soluble ionic solids are strong electrolytes. Something like sodium chloride is going to dissolve and dissociate in solution. So you've got tons of sodium ions and chloride ions, and that will be an electrolytic solution. Soluble ionic solids are strong electrolytes, but you can also have covalent compounds that are strong electrolytes if they also dissociate to form ions. And so we know that Bronsted-Lowry acids and bases can do this. However, this says strong electrolyte, So we need a strong acid or base, right? We need something that is going to ionize to completion. So do we have any strong acids here? So ammonia is a very weak base. This is not particularly acidic or basic, not acidic or basic. This is amphoteric like water, but not tremendously acidic or basic either. But hydrobromic acid, or this is hydrogen bromide, but as a gas, if you put it in water, you've got hydrobromic acid. That's a very, very, very strong acid. So that one works. We're going to put E right there. You put HBr in water, it will dissociate to completion, giving you only bromide ions, and then it'll protonate water molecules, so you'll have a bunch of hydronium. So number 3, slowest to effuse through a small opening at room temperature and atmospheric pressure. Effusion. Diffusion and effusion, we're looking at the movement of molecules. Effusion is the one where they're moving through a small hole, like a pinhole or something. But regardless of the type of motion, we need to understand that the heavier the molecule, the more slowly it moves, right? So very tiny, very light things like hydrogen, helium, they go very, very, very fast. And then the heavier the molecule, the slower, or atom, or whatever it is, the slower it's going to move. So what this is really asking, slowest to effuse, is really asking which one is the heaviest, right? So certainly not H2. These are pretty light. This has a sulfur atom in there, so that's getting a little bit heavier. But HBr, that's got bromine, right? That is definitely the heaviest, and so that's going to be it. So HBr is the heaviest, so we've got E for that as well. We ended up using that one twice. So again, these are really good looking at a periodic table, whether you have some groups or you have some substances, and you need to talk about their properties, assign them to certain statements. And we talked a bit about Vesper, electrolytes, and effusion. Okay, for this one, we have some reactions. We have 5 reactions here, and we want to assign them to these statements. So the first one says a precipitation reaction. We're looking for a precipitation reaction. So what does that mean? Remember, a precipitation reaction is one in which we have ions in solution. So we have aqueous ionic species, and they come together to form an insoluble solid and therefore crash out of solution. So we need aqueous ions forming a solid, right? Definitely a precipitate is a solid, so we need to see a solid on the right side. So what do we have here? Well, okay, this one is, we're forming a solid, but this is a solid, this is a gas. Those are not ions in solution, right? Over here, we've got aqueous lead 2+, we've got aqueous chromate, and then we're forming this a solid. So this is it, right? This is our precipitation reaction. Boom. Here, this doesn't work. We're forming aqueous species. Here, we're forming gases. Here, we have an aqueous species. So you look straight for the solid product. We had 2 of them, and then the first one just didn't make sense because we didn't have aqueous ions in solution as the reactants. So number 2, a Lewis acid-base reaction that produces a coordination complex. So what is a coordination complex? This is one where this is a compound where we have a central metal ion, a central metal atom with some oxidation state and ligands, some number of ligands that are coordinated to the central metal atom. So if we don't have a central metal atom, that doesn't, it's not going to work. It doesn't make sense. So here, C and D, there's not even any metals at all, so that doesn't work. A and B, there's a magnesium atom and a lead atom, but these are not, there's no ligands, right? This is magnesium oxide. That's an ionic compound, right? It turns out the only one here is we've got silver, and the silver has these 2 ammonia ligands. So this is our coordination complex. So 2 is going to be E. Then number 3, an oxidation-reduction reaction that is also a synthesis reaction. So redox reaction, we know that there's going to be an exchange of electrons. Something is oxidized, something is reduced. There is electron transfer going on. But a synthesis reaction is one in which we have 2 things becoming one thing. right? So anything that's not two things becoming one thing is not going to work. So C does not work. D does not work. E is two things becoming one thing, but that's not. This is not. This is not redox, right? There's no change in charge. We've got ammonia ligands; they just coordinate, right? So that's not redox. No, part B looks this you might get tricked by it, but remember this was a precipitation reaction. There's no electron transfer happening. We've got a 2 plus cation, a 2 plus anion, and then they hang out together and crash out a solution. So there's not any electron transfer that's happening, right? These still bear formal charges. But option A here, this works because if you assign oxidation, first of all, it's two things becoming one thing, so that's synthesis. But then remember, elements have oxidation numbers of 0. But then over here we've got a compound, and oxygen is always -2, except for peroxides. But so if that's -2, then this is +2. So magnesium has been oxidized by oxygen, go figure, and oxygen has been reduced. So that is a redox reaction and a synthesis reaction. So that one is going to be A. So this is very nice because this is helping us remember the definitions of these types of reactions, right? What is a precipitation reaction? We need to know fundamentally what that means. We need to know what a coordination complex is. We need to know what a Lewis acid-base reaction is, right? We actually didn't talk about that, but this is a Lewis acid-base reaction. The silver plus ion is a Lewis acid because it is an electron pair acceptor, right? Ammonia has a lone pair that is going to coordinate to the silver ion. That's a Lewis acid-base reaction, unlike Bronsted-Lowry, which is proton transfer, right? It's still an acid-base reaction. And then what is a redox reaction and what is a synthesis reaction? So these are some good reactions, and we went over some important definitions. Okay, here we have an interesting visual problem, a little bit of stoichiometry. This says the reactants represented above are placed in a vessel and a reaction occurs. Which of the following best represents the contents of the vessel after the reaction has proceeded as completely as possible? So this is going to completion. Now, so what do we have here? We've got hydrogen atoms, carbon atoms, and oxygen atoms. So here, this is clearly CH4. We've got methane, right, carbon and 4 hydrogens, and then we've got O2. So we've got methane and oxygen. So this is a combustion reaction, right? When we're reacting a hydrocarbon with oxygen, that's a combustion reaction. And any combustion reaction, we're always going to get CO2 and H2O, right? So now we do want to balance this. So let's take a look. We've got 1 carbon over here, 1 carbon over here. That looks good. We've got 4 hydrogens and only 2 hydrogens, so let's put a 2 right there. And then we've got 1, 2, and then 2 more. Right? We've got 1 oxygen per water, so this is 4 oxygens total here. So we can just put a 2 right there. And so this is the balanced equation for what is going to be going on, the reaction that is going to happen in this vessel. And so certainly we want to see CO2 and H2O in the vessel after the reaction is done. So looking down here, we've got here's some CO2 and water. Here's some CO2 and water and some oxygen. Here's some CO2 and some water. This one is the only one that absolutely doesn't make sense. We're not going to get C2 and H2. This is blatantly false. So here the thing is we have to do a little bit with stoichiometry here. We have to think about limiting reagents, right? Because we have we're looking at 2 methane molecules essentially. So how many oxygen molecules can react with 2 methane molecules? Where we need 2 oxygen molecules for every methane, and we have 2 methanes, so we're going to need 4 oxygens. So let's just put numbers up here. See, we're doing something very reduced. Obviously, when we really do chemistry, we don't count individual molecules, but this is just sort of making it very simple for us. So 2 methanes, we're going to need 4 oxygens, right? And that is going to produce 2 carbon dioxides and 4 waters, right? We have a 1 to 2 to 1 to 2 stoichiometric ratio, right? That's what these coefficients are telling us. So 2 methanes and 4 oxygens, make 2 CO2s and 4 waters. So what that also means is that after we use 4 oxygens, we are going to have 2 O2s left over. So oxygen is our reagent in excess, right? Methane is the limiting reagent. Oxygen is our reagent in excess. So what we want to do is we want to find the one where we have 2 CO2s and 4 waters. But then we also need to have those 2 oxygens left over. So here, this doesn't work because we don't find those oxygen, the excess oxygen. Those can't have disappeared, right? Law of conservation of mass. They have to still be in there. And then D, likewise, this doesn't work because we suddenly 2 extra carbon atoms appeared out of nowhere, right? We had 2 carbon atoms and now we have 4. That doesn't make sense. We didn't just get 2 carbon atoms out of nothing. And so this works because we've got our 2 CO2s, we've got our 4 waters, and then we have the 2 O2s left over, the excess from, that's the O2 that didn't get reacted. So this one is definitely C, and this is a nice little problem because it allowed us to balance an equation. It made us think about limiting reagents and reagents in excess, made us think about stoichiometry, and it did it in this nice visual way where we could really, make a prediction and then look at the answers and see the subtle differences between some of these ones that are trying to throw you off by omitting a reagent in excess and things like that. So that's C, and that's the answer to this one.